Hey there, awesome physics students. Let's talk about the phenomenon known as weightlessness. First, let's start in a very ordinary place. We'll start in your bathroom with the bathroom scale so we can know what the bathroom scale does. So you stand on the bathroom scale and you weigh yourself in the bathroom. And of course, in this case, the two forces on you are the normal force up because you're touching the bathroom scale. That's the force with which the bathroom scale is pushing on you up. And then there's the force of gravity acting on you down. And so let's go ahead and use our problem-solving framework for this. We'll note that the acceleration in your bathroom, at least while I'm weighing myself, my acceleration is 0. So then we can choose a coordinate system in any direction. Let's use a standard XY coordinate system. And we'll sum the forces in the Y direction. And so using the free body diagram to get this equation, we get normal forces up. That's a positive force or a positive component. And then gravity is down, so that's a negative component. And those are the only two forces acting on me. I set that equal to ma in the y direction. But I already said that my acceleration is 0. So this is 0, which means that the normal force minus gravity is 0, or the normal force is equal to the force of gravity, or my weight. So this is why in the bathroom we stand on the scale. We, of course, interpret the bathroom scale as telling us our weight, but really this number is how hard the scale is pushing on you, and you can tell that easily. Just pick it up and push down on it, or stand on it and kind of push on it quickly. You'll see that you can get that number to change. So how else could we get that number to change? Well, let's imagine that you take this bathroom scale into an elevator, like lots of normal physics students do. They take their bathroom scales into elevators. And so you do this, and of course the same forces are going to apply to you. You're going to have the normal force up on you from the scale again, and the force of gravity. And we'll use the same coordinate system here. But in this case, you go into the elevator and you push the button to go to a lower floor so that your acceleration will be down, or in the negative y direction. And so if we sum the forces in the y direction, again, following our problem-solving framework here, we get the normal force as a positive component and gravity as a negative component. It's the same result we get over there. We set that equal to ma in the y direction, but a points down, and that's a negative acceleration because it points opposite the positive direction that we defined. So this is a negative number. If this is a negative number, that means when I add these two together, this force of gravity must be bigger than the normal force, right? If it's going to win. And so how do we interpret that? Or what does that feel like when we go into the elevator? Well, you feel funny, right? When you go into the elevator and you push the button, you accelerate down just a little bit. You feel a little bit in your stomach maybe. And of course, really what's happening there is it's your vestibular system in your inner ear that detects acceleration, and it sends those signals into your brain saying, something's going on, I feel funny. Sometimes we interpret that as located here, but it's not located here. It's in your inner ear. That makes us feel like we weigh less, or feel some weightlessness. But that I'm going to put in air quotes because that's not true. The gravitational force is still the same as it was before. We're on the same Earth, and we have the same mass as we did before. And so really what's changed is the normal force has become less. And so you can see this if you imagine taking this to its logical extreme here. Imagine you're in an elevator, and at this point it's an amusement park ride because we're going to make the acceleration g down. So you're in free fall. And so what do we experience that like? Well, you can go to an amusement park and experience that, and you really, really feel it there. In this case, we can write the same forces on us, normal force up and gravitational force down, and we sum the forces in the y direction. By now, we can easily do this with our eyes closed. Normal force minus the force of gravity. But in this case, if the acceleration is down, g, that's a negative g, right? According to our y direction, that's a negative number. And so this tells us, of course, the force of gravity is mg. And so if we write this out, normal force minus mg equals negative mg. We could add mg to both sides, and that tells us that the normal force equals 0. So physically, what's going to happen here is that your feet are going to temporarily lose contact with the scale. The scale will read 0. And why it reads 0 is that the elevator is accelerating down with g, the scale is accelerating down with g, and I'm accelerating down with g. And we're all accelerating together. We don't need to touch each other. We don't need any more contact forces to maintain that state of motion. And so the normal force is 0. Of course, if this happens, the acceleration is g down. You feel weightless, but remember that the gravitational force is not 0. You are not weightless. What's happening again is your vestibular system is saying, it's acceleration, some incredible acceleration. It feels funny. It feels weightless, but it ain't. Now, you can simulate this if you have a lot of money. If you get into an airplane, there's specially built aircraft that will travel in a parabolic trajectory that is in free fall. And when it is in free fall, your acceleration will be g down, and the airplane will be accelerating with g down around you in this parabolic trajectory, and so will you, and you will feel weightless. But you are not weightless. It's just that your vestibular system is telling you feel weightless. You can easily experience this at home. Stand on a chair and jump off, and when you jump off, for that very tiny amount of time that you're in the air, you're going to feel weightless. Okay?